I want to talk about exponential models. Exponential models are used to model any type of explosive growth or rapid decay. So you heard of exponential growth and exponential decay probably. This is what this video is going to be about. Um, this is really just one model for modeling all of these or both of these types of situations. So you could use this, for example, to model the amount of carbon dioxide in the atmosphere over the past 50 years. You could use it to model how money usually grows. You could use it to model views of a viral video, so how that's growing. You could even use it to model how a drug leaves the bloodstream after you ingest some drug. So there are two basic ways of writing down this type of model. Even though it's just one model, there are two different ways to write it down. And I want to spend some time talking about how to go back and forth between the two models, because both are really useful in their own setting, but one is a little easier to understand intuitively, and then the other one is a little more powerful scientifically, more powerful for analyzing things. You can be more precise with it. So first, the one that's more intuitive, usually this one is written down something like this. The amount that you have after t hours or t days or t years is equal to the initial amount, which is written usually with a sub 0 to indicate that you're starting at t equals 0 there. So the initial amount times 1 plus the rate, in parentheses, raised to the power of t, whatever that time value is. And here r is the interest rate if we're talking about money. So you can think of it as the percentage of the amount of stuff that's growing each year or each hour or each day. If we're talking about carbon dioxide in the atmosphere, then how fast is that growing in terms of percentage that you started out with per year? The other way to write down this model that's a little more powerful but less easy to understand what the numbers represent looks like this. The initial, or the amount after t years or t days or hours, is equal to the initial amount times e to the kt. And e is just a number here like pi. Instead of pi is about 3.14, this one's about 2.72. It's just a special number that we use. It's irrational like pi. K is just some constant. It's not easy to describe it intuitively, but it's just some number that's associated with this model and this quantity that we're measuring. So we want to be able to go back and forth between this rate and this e to the k somehow. The way to do that is to rewrite that second equation, rewrite e to the k in parentheses. It still equals the same thing. And now you can see, if you compare the left equation and the right equation, they're the same equation. It's just that the stuff in parentheses is written down differently. So you can set the 1 plus r on the left equation equal to the e to the k on the right equation. And then if you know what k is, you can easily solve for r by subtracting 1 from both sides. Or if you don't know what k is, but you know what the rate is, and you want to go and see what k is, you can just rewrite this equation in its logarithmic form. So log base e, remember, is written as natural log. So this would say log base e of 1 plus r equals k. So we'll write it as k equals natural log of 1 plus r. So again, both of these representations of exponential models are very useful. The rate is a little easier to understand, the r, because it's sort of an average over an amount of time. But again, the other one allows you to look specifically at the growth rate at a moment in time, an instantaneous growth rate, not an average over a span of time. So now you know how to go back and forth between these two representations of the same model.